Okay, thank you, cloud person in the data center. All right, so why don't we get started? Hi, the meeting controls. Let's make sure this is live. Okay, yes. All right. So good morning again. Today we're going to spend the bulk of the time talking about file systems. And with that, we'll also look at the so-called command line and talk about directories. And the reason for that is that in the past, many students, including computer scientists, have struggled with these ideas and these concepts. And so among the faculty, we felt it important to include modules explicitly about this because as I understand, at least in the computer science and data science curricula, there's no requirement for operating systems, which is really, really important. It's really important to understand the machine, even if you never are in the business of modifying operating systems or implementing server infrastructure. It's really still important to understand how the machine itself functions because it makes you more conversant in writing solutions that run on said machines. Okay, but before we begin, some administrative bits. The reading has not changed. As I said before, I do not test you on the reading. I treat you like the adults that you are. The deadlines are there for your benefit for pacing on keeping up with the material. A lot of material that I curate will not be from the book. Last time I taught this last semester, we had, I think it was 4 books. I don't like to participate in the financial extortion that is textbooks. And so I try really hard to keep the costs down on the textbook. And so the Python for data analysis is the primary text that we will have. And it's also available as open access, which means web-based version. The URL is on the Canvas site, is available for you if you choose to have bits over atoms. But if you like atoms, which I do, I like paper, something about feeling the paper, turning the pages that just, feels warm and comfortable for me. You're also welcome to purchase it. I'm not supposed to say it, but you can get it much cheaper from other sources outside of the campus bookstore. All right, question. Yes, I got a Slack message. Did you send me that message? Okay. So the TA hours. Diana and Elizabeth are our TAs. We're fortunate to have 2 very talented young people as TAs for this class. They are students, and I usually give them the first couple days, so the last 3, 4 days of the semester, to let their schedules settle before they choose their office hours. So that should be coming out soon this week. I've actually sent that message to arrange with them. Okay. Question, yes. Ah, I didn't delete that. Okay, I thought I deleted that. That's the test project doesn't matter. That's for my benefit. So, like you, I'm learning Canvas. They pivoted among the faculty, and between fall semester and spring semester, we only had 2.5 weeks to learn it. And so that test project, thank you for mentioning that, is just there for my benefit because I didn't know how to create a project before that. I thought I deleted that, so I'll delete that. But project one is on the Canvas site. That is live, and I recommend you look at it sooner rather than later. The submission for this class is all electronic. I like to run my courses digitally, and that's something that is an artifact of my previous institution. We pivoted to a digital campus 2 years before COVID hit. So our pivot was seamless, half a week to being online when the shutdown occurred. Are there any other questions? Yes. Um, Great question. I'm going to say no, because the whole purpose of this is for you to learn to do it the hard way, and then we'll use Pandas to do it the easier way. But thank you for your question. Did everyone use Pandas in 120? No? Okay. All right. And so, unfortunately, you're going to have to use NumPy and slicing and things like that. The purpose of this project is twofold, to give you some exposure to data wrangling types of issues, but also to help refresh your practice with Python semantics and programming. Okay. Any other questions? No questions? No? All right. So again, as I said before, the structure of the class, the Monday and Friday sessions are going to be more class sessions, and I reserve the Wednesday for the practical component, lab exercises, and things like that. Only the first class meeting last week, Wednesday, was more class session because it'd be weird to have a lab first day. Okay. Any last questions? Yes. Mhm. The research notebook? Yes, yes. Yes, and the resources you collect. Because one of my goals this semester, or at least in this class, is to also empower you to be able to find information, right? As you'll notice, there's lots and lots of information in lots of places about Python and various Python isms, and I want you to be able to go out and find this stuff for yourself. Over the 15 weeks of the semester, I can't possibly teach you everything about Python and everything about data analysis and machine learning. And so what I do is I survey a bunch of examples from key topics, but then after that, you're left with searching for things yourself. And so I want to get you in the habit of, in your problem solving, to be able to find information for yourself. It's a really important skill, not even just for this class, just in general for your careers. Okay. Any other questions? No questions? Okay. And so for project one, you're able to collaborate in a group of no more than two individuals. And I ask on your written material that you please put the names of both people so that I can do the proper attribution. All right. No last questions? Yes, yes. You both submit it. And the reason for that is it makes it a lot easier on me for the automatic grade book. Okay. Any other questions? No? Yes. Yes. But your reflection is different because what you learn from it is not going to be the same. And so there is a unique component regardless of your collaboration in a group. Okay. Any other questions? No? All right. So please make sure you're registering for the Slack channel. I won't send emails, and I ask you not to send me emails. Use direct messages on Slack for things of a personal nature, academic nature. I get about 100 plus emails a day, and it's very likely I'm going to miss something important. So using Slack helps me best to help you. If you have a question about the material for the class or in general about the class, please use the group discussion Slack channel. It allows me to leverage my answer to you because I find at least a third of your colleagues in the class have the same question. Okay, so if you're not registered, I know who you are, you know who you are. Please make sure you get on Slack. Okay. Any other questions? Yes. DSCI 125-304. Yes. Yes. And for those of you who are registered for 125, it's also a co-registration with a 304 section for graduate students. All right. Any other questions? No? No questions? A little quiet. A little tired? Want to be someplace warm? Good food? Yeah? All right. I hear you. All right. So we last left off, to jog your memories, we talked about the data science process and we gave an example for our fictitious spaghetti and meatballs index. And we gave a visualization registered in time. Along the horizontal axis, you'd have something like time. And along the vertical axis, you'd have cost in whatever dollar unit or what have you desire. And if you observe something like this, you'll notice that in the graph for the SMBI index in the blue, and higher is more expensive in this chart, you'll notice that there's an increase in slope, a dramatic increase in elbow, so to speak, in the graph. And so a natural thing, as we discussed, to ask yourself is what happened here? And there are certain factors that influence this increase in this particular statistic, this SMBI index. And one of the things you would do in the data science process is to enterprise to figure out precisely why. So you can posit or guess or hypothesize some things that might be responsible. And then it's up to you to go off and find corroborating information that confirms what your theories are about what might be the cause of this. And so in this example, we said the oil price climbs, and we asked ourselves, what does oil have to do with spaghetti and meatballs? And one of your colleagues in the class, when I asked that, said, well, oil increase in oil corresponds to an increase in gasoline. And we talked about this supply chain. One of the derivatives of oil is diesel fuel. And we said most of the goods that are circulated throughout the US travel in this 18-wheeler transportation modality by truck. And so if the cost of fuel goes up, so too does the cost of trucking, and that cost is passed on to you in the retail at the register. Okay, any questions about this? Now, of course, this seems obvious, right? But we can't always rely on our intuition. We want the data to tell us what these dependencies are. And one of the things that we'll talk about in one of the modules of the course, or several, are so-called variable couplings. We want to calculate what the strength of association is for various measurements that collectively comprise our data set. That's really, really important because that's part of your uncovering these insights, these non-obvious or these hidden or these latent interactions between your data or parts of your data. Okay. Any questions? Does that make sense? Yeah. All right. And so you can certainly collect evidence. Are there charts? Are there pieces of information? This particular chart is a stock ticker corresponding to the crude oil industry. And we can see, or at least we saw in that example, right around the same time, we saw in crude oil spike. Now, certainly, it might not spike at the same time. It might spike ahead of the increase in this food item. It might spike behind. Whether it leads or lags is another calculation that we're going to talk about when we talk about the Baltic Dry Goods Index. And so with these couplings, these linkages between your variables that comprise your data, these linkages might not be direct. They might be leading, they might be lagging in time. And it's also up to you to determine what this lead and lag is. And fortunately, Python gives us the ability to traffic in time and to shift data that's measured in time in order to make such calculations. Any questions? Does that make sense? Yeah? All right. And so we also went to some economic indicators, some statistics, and it did confirm for us that inflation absolutely did spike, and 10% inflation is absolutely huge historically. And yes, the price of spaghetti and meatballs did get out of hand, and it coincided with the increase in oil. Okay. Any questions? Make sense? No? All right. And so we said when we communicated, according to the SMBI index, what this statistic or this model that we created, yes, it did get out of hand, and we saw a spike coincident with the run-up of oil prices, but we're not done. As part of our analysis, we need to ask further questions to try to uncover what the dynamics, what the behavior is of this increase. Because if this thing can go up, it can also go down. And armed with the knowledge of what factors influence its change, whether up or down, we can also talk about what we believe will happen in the future when certain things decrease. Okay. Any questions? No? No questions? No, quiet. Okay. So let's pivot to talk about things that are not so much practical, but to give you more of a background from a computer science perspective. Because while this is not a computer science class, understanding the machine and the tools and why they're important is going to be very, very helpful to your career. Okay. And so we're using Python. And as I said at the first class, the two major platforms or languages used for data science are R and Python. And so we choose Python for this course because CS120 is in Python, and why not use the same language? And Python is more widely used among the computer science crowd, whereas R is more widely used among the math crowd. So we're using Python for this reason. So you start out in Python with your source code, and it's just a text file, nothing special about it. And the only reason for including this .py in the name, this extension, is just really for your own benefit. Certainly, some operating systems will associate certain programs with a file based on what this extension is, right? So things like Mac OS will paint the right icon for it. Some of them will leave a link to it, so a link to the program, a certain program, so that when you double click, it'll run that program and give it the contents of that text file. But this text file doesn't really matter to anyone except for the Python compiler. Now, CPython is the name of the compiler that understands Python. It's the default that's produced by the open source community, and it represents the official version of Python on record. There are absolutely all sorts of weird extensions that people try to create, but the official Python is put out by the organization, the open source organization for Python, and it is the CPython compiler. Now, I say compiler specifically, and some of you might have learned the term Python interpreter. The interpretation part happens with the so-called bytecode. And so we take this Python file, and that's the Python statements for correct Python, the syntax and the semantics that you've all learned, some of which you've learned in CS120, and you compile it. And it's compiled into bytecode, which is the binary equivalent, the ones and zeros of these commands and these statements for these blocks of behavior that you sequence together. Now, this bytecode is a file, and oftentimes this file is hidden from you. But on many platforms, primarily the Unixes, you get to see what this intermediate file, this bytecode, looks like. Now, this bytecode is interpreted by two things. One is the virtual machine. The virtual machine is where the behavior comes in, the semantics. And I really, really encourage you to learn how the VM works, because that's what gives rise to the semantics, the behavior associated with these commands. And knowing these idiosyncrasies of the behavior helps make you a stronger modeler and a stronger programmer. Any questions? Does that make sense? Yes.
So what is just-in-time compilation?
Let's talk about that in just a moment after I finish this statement, because it fits into that. And I'm glad you asked that. So, one of my favorite topics. So this virtual machine has a bunch of routines written, and it's often written in C. And it takes each one of these sequence of ones and zeros that's meaningful to the VM, and it calls these functions. Also, we have system libraries. The system libraries are implementations of useful things that people need in the course of writing their programs. Now, to your question, when you interpret these sequences of bytecode that have meaning, that's calling functions within the VM runtime. It's the collection of programs in their executable format that give the behavior to each one of these constructs in the language, like iteration or looping, conditionals, breaking, returning, parameter passing, and all of that good stuff. Now, this interpretation can be very, very slow. And it's recognized that when you want something to run very fast, well, you want to run it natively in the binary format for that particular processor. So if you're running on an Intel processor or an AMD or Motorola processor or what have you, the fastest executable code is in the native bytecode, the ones and zeros that are meaningful to the actual chip itself. Now, this bytecode is called bytecode instead of binary code because it's meaningful to the virtual machine. And at the end of the day, the VM or virtual machine is just a process, a program that's running on top of your operating system. So there's a level of indirection here, and therefore it's slow. Now, what this JIT or just-in-time compiler does, it says, okay, let me analyze the statistics or do the accounting for all of the functions that are being called in the course of executing a program. And those functions that are called the most are the so-called hotspots, right? And these hotspots, if you want your program to run really, really fast, take these hotspot functions and convert them to the native code of the underlying processor on the machine. And that's JIT or just-in-time compilation. Okay, now just-in-time compilation, Sun Microsystems, where I worked in another lifetime, many, many years ago, we worked on the JIT, just-in-time compilation, and it was done to speed up Java bytecode execution. Okay. Any questions? Does that make sense? All right, no questions? And so we have our system libraries and our virtual machine. Together, they form the runtime, and this gives the behavior to one of these constructs that you learn. And of course, the result is your running program. Now, of course, there are many different choices that you can make for your runtime. You can, out of the box, use, say, Python 3.10 or 2.7 or what have you. And you can change lots of things for your virtual machine and for your system libraries. And so when you change the virtual machine, you're changing the Python language itself. You'll notice, or maybe you didn't, I encourage you to look at the history, that there were changes to the behavior of Python from the version 2x version of Python and the version 3.x version of Python. Now, whenever you change the basic language, you're changing aspects of the virtual machine, that portion of the runtime. Now, when you change the system libraries, sometimes you're adding new capabilities, the ability to compute scientific functions, or you're making fixes to these libraries. And so with our runtime, this collection of both the system libraries and the VM, it's really important when you're developing software to decide what tools and components you need for the project that you're enterprising to build. And so, oops, uh-oh. The libraries that we'll use over the course of the semester include NumPy, and NumPy takes the base level Python. Python 3 is what I'm using. Hope you're using that too. And NumPy supplies implementations of useful operations with n-dimensional arrays. In Python, you can construct n-dimensional so-called Python arrays, but NumPy implements them as well. On top of that, and it adds useful things like flattening, transpose, and all sorts of other types of operations. So we'll be using NumPy in project number 1. There's also something called SciPy. Now, SciPy takes parts of NumPy and other parts of Python, and it implements so-called scientific computing functions, all the good stuff that you will learn about if you haven't had it yet, like linear algebra, optimization to minimize or maximize a function. Really, really important in machine learning and a lot of other types of application domains. And so the SciPy is something we'll be using because it also implements various statistical routines, things like hypothesis testing, sampling from various distribution families, etc. Any questions about this? Does that make sense? No? All right. We'll also be using Matplotlib. That is a graphics library that allows you to compute and display various types of visualizations, things like histograms, scatter plots, lines, etc. There's another visualization library that we won't be using, but I just thought I'd put it out there, Seaborn. And Seaborn takes Matplotlib and makes it much more pretty. Seaborn can do more sophisticated types of visualizations. We'll also be using scikit-learn for the machine learning APIs we'll be using, those examples this semester. And scikit-learn is built on NumPy, SciPy, and Matplotlib, and it's used for extracting insights, these models that I alluded to before. And Pandas, which you had mentioned, Pandas improves upon these n-dimensional arrays, and it makes it really, really easy to traffic in things that include time constructs as well as arbitrary data tables. Any questions about this? No? So these are system libraries. And if time permits, we'll get a chance, this is if time permits, to use something called TensorFlow, which is a graph-based mechanism for neural networking. A tensor is the generalization of an n-dimensional array. And it's called TensorFlow because how you train these neural network models is based on tensors, multiplying matrices and vectors and propagating those results. And then Keras is built on TensorFlow, and it makes it easier to construct these categories of models, these so-called deep network machine learning models. Any questions? Does that make sense? And so we have all these libraries, and this is just barely scratching the surface. You think of it, someone has created a Python library. There's a library for that. And so when you build any kind of data product, yes, you're following the data science process, but you have a lot of different versions of Python and libraries, which together form the tool chain that you're going to use to implement your project. Now, of course, if there's a capability in a new library, you're going to include that. Or if there's a version of Python and they're always adding little nuanced changes to Python, if there's a version of Python that supports something you need, you're going to use that. And so you have all of these so-called dependencies that your code or your system or your data product needs. Now, of course, sometimes you're going to change this. Let's say you want to build a different data product. You're going to use, for example, a different version of NumPy. Instead of version 1.2.3, and I just made that up, you might use 1.3.3 because some new capability or some bug fix occurred with that change in library. So your tool chain can change depending on the data product that you build as a result of this data science process. So this can get out of hand really quickly, especially if you're dealing with this experimentation mode of conducting your work. So the first thing you do is you find and install your dependencies. that you need to build your data product. You go ahead and you install them, and you're gonna, maybe there's an obscure blog post somewhere on how to install it. That's why it's important to have a research notebook. You build your new data product, you discover some insights. These insights lead you somewhere. And then you might ask, well, what do I do next? What about this other thing that I should be exploring? So then you decide, okay, well, I'm going to uninstall all of these different components, the libraries, version of Python, and I'm going to find and install the dependencies for this new data product that I'm building. So you're going to do this over and over and over again in practice, in industry, or in the marketplace. And so managing all of this can be really bad for your system. It's both hard to manage as well as quite cumbersome. And so there's certainly a solution for this, Conda, or its full name is Anaconda. And Anaconda is an important open source package. And one of the most powerful things that Anaconda does is provide what's called a virtual environment. And a virtual environment is a named collection of dependencies, of tools and libraries that you collect together and you associate with them with a name. And when you run Anaconda, you start Anaconda, and then you give it the name of that virtual environment. And then all of a sudden, it pulls in all of the dependencies that you need for that data product. And so if you're working on something and you have 5 different data products you're building, you might have 5 different sets of dependencies, and Anaconda very, very gracefully helps you to manage all of this. And you can do that by name. Any questions? That make sense? And so one of the things you'll be doing is installing Anaconda, and I have the instructions on the course resources section of the Canvas site. I almost said Moodle, of the Canvas site. And it runs on all the major platforms, Mac OS, Linux, and Windows. Any questions? No? So please make sure you also get set up with Anaconda. The instructions are there on the Canvas site. All right. It manages collections of named components. It maintains a list of your dependencies. You can set to these virtual environments, and it pulls in everything you need for it. And it makes your development cycle easy, with an emphasis on easy, right? It is an absolute mess to have to go out and manage all of these dependencies yourself. It's a recipe for failure. And you want to keep your attention span focused on the data product, not on all the systems issues about managing your dependencies. So I really strongly encourage you to become conversant in these sort of tools, because if you enter the marketplace in data science, that's what people are really using. Okay. Might not be Anaconda, it might be something called Docker, which we won't talk about, but it's certainly some tool that people use to manage all these things. Any questions? Does that make sense? Yeah? No questions? All right. And so PyCharm is another tool that we'll be using. Has everyone used PyCharm? Or do you use PyCharm? Did you use it in 120 or the prerequisite course? PyCharm is a so-called integrated development environment. It looks like an editor and allows you to write code, but unlike a text editor or some document editor, it treats your Python program as a database. And what I mean by that is not just your text. Things are chopped up and processed, and it's analyzed to make you more productive. And so if you start the name of a function, when you type it, it'll bring up a help page to show you what the interface for that function is. Also, it includes a debugger, and a debugger allows you to step through statement by statement in Python, step through your program, and allows you to interactively view the intermediate results as your program is running. And so it's really important to use a debugger, particularly as you come to use some of these APIs that I just mentioned for these libraries in Python. It really helps you to be more productive. And so this idea, and I know when I was in your position, when you learn a programming language, they say, oh, to debug it, you do a print statement, right? That does not work, especially when you're dealing with so-called multi-threaded applications, right? You really want to use a debugger. And in fact, when you go out to interview, for those of you who are enterprising to enter the workplace after graduation, it's really important also to have an understanding of the popular tools that folks are using in your discipline. Any questions? That makes sense? No questions? No? All right. And so the nice thing about PyCharm, and most of the IDEs do this, is it plugs directly into the Anaconda virtual environment. So if you switch to a different project, as it's called in the IDE, which is a particular product you're trying to build, you can, within the IDE, set the virtual environment. And then underneath the covers, Anaconda will switch in and switch out the right libraries as well as version of Python. Okay. All right. Any questions? No? No questions. All right. And so there is a link I've curated on the course resources section for installing the documentation, also for using Anaconda as well as PyCharm. And the good news is, if you're a student, you have free access to the professional version of Python, which is what the developers use in industry. Any questions? No? No questions? Yes. Ah, the big difference is some of the analytical tools. I don't know exactly what that list is, but when you deal with professional versions of things, I can get you that list. Things like profiling is included. And profiling means it does all the accounting for the different functions that you're calling, and it tells you what's most frequently called. And so beyond just running your program, analyzing the performance gives you the opportunity to speed things up. And that becomes very important when you traffic in really large data sets. Okay. So there are those tools as well as things that plug into version control like GitHub and other things. But the real thing you get when you're dealing with a professional version are all these productivity tools just beyond writing programs and debugging programs. But I don't have the full list off the top of my head. Any other questions? Does that make sense? Yeah. All right. And so you install Python, you install some other components, you install Anaconda and register for something called Anaconda Nucleus, which is their online environment. It has a web interface and it allows you through just pointing and clicking to install other components, including PyCharm, if you choose to do it that way. All right. So any questions? Last questions? No? All right. So we talked about CSV files. And in that, we said generally that there's data. And we talked about this idea of the so-called data deluge. Regardless of the industry that you're in, it could be public policy, it could be urban management, it could be computer science, it could be retail, what have you. It's inevitable you're going to have to deal with data. And of course, with this data, data arises in various types. And so I thought it important to talk about these data types. And so one data type, so-called categorical data type, refers to general objects. And so in the world, objects have labels like cat, dog, truck. And the things that we label is associated with the appearance of these objects, as well as the behavior of these objects. So there's a semantics associated with these labels. And these labels describe distinct categories, hence the name categorical variable. And so in a data set, we might say animal equals cat or animal equals dog, okay? Now, categorical variables can be so-called nominal, meaning they have no natural ordering. Absolutely, you can order it in lexicographic order because we have rules for that. But natively, if you have a cat object and you have a dog object, there's no rule that says one has to precede the other in some ordering, right? They can't really be put in some natural ordering. Any questions? No? There are other type of categorical types, and you'll see this arise all the time. For every example, there's a nuanced counterexample. Some categorical variables are so-called ordinal. They have a natural ordering associated with them. In this example, we have movie ratings, and these movie ratings go from G through NC-17, and that has to do with the amount of adult content in these movies. And you can right away say, this one comes first, this one comes last. You can do it in non-decreasing order or non-increasing order, right? But naturally, these objects themselves have an ordering. Those are so-called ordinal categorical variables. So we have nominal and we have ordinal. Any questions? There are other types of variables that are numerical in nature, so-called quantitative variables, and they take on numerical values. Now, these numerical values, because these values are numbers, there's a natural ordering to them. And so, for example, if we have measurements like elevation or we have measurements like the volume for liquid containing storage tanks, we can naturally order these measurements, 300 gallons, 500 gallons, 1,000 gallons. And so these numerical variables can arise in two different flavors. One is so-called continuous. Let me not fall and hurt myself. One is so-called continuous, and one is called discrete. And the distinction is these continuous variables, you can think of them as being real value. They're so-called uncountably infinite. And uncountably infinite quantity is a type of number such that you cannot enumerate and list out all the different values. If I were to give you a temperature 35 degrees and 36 degrees, you can think of something in between the two. If I were to give you 35.5 degrees and 35 degrees, you can always think of something between them. And you can continue to divide and divide and divide this, finding these numbers between, and it goes on infinitely. You never reach a bottom where you can list out the individual numbers when they're real value. So that's what uncountably infinite means. Discrete means it's so-called countable. Now, you can be countable and still be infinite. What countable means is that you can associate a natural number with it. The set of natural numbers refers to things you see in nature. I see one cow. I see two flowers. And you're associating a natural number with each one of the objects in this number system. And whether it stops, it is finite, like 1, 2, 3, or it's infinite, it goes on, you can still associate a natural number with each item. And so that's what discrete means. It means it's countable. Discrete doesn't necessarily mean it's finite. It has an end. It means it's countable. Any questions about this? Does that make sense? All right. And so there are a lot of nuanced differences. Direct your attention to the graph on the right, on the left rather, your left. In my mind, I kind of automatically flip it. And here on the horizontal axis, we have a categorical nominal graph. It doesn't matter if we have women followed by men or men followed by women. And on the vertical axis, we have counts, right? That is finite. It's countable, numbers of people, okay? In the center here, along the horizontal axis, we have the age of a car in years. And in this particular case, you can assume it's a whole number. So that's countable, numerical value, quantitative. And on the vertical axis, we have price. And price, you could think of as real valued, but people don't really say $0.00001. We talk about cents, which is 100th. And so you can effectively count this, but it is a quantitative variable. So there's a nuance there. And then lastly, on your right, we have another graph. You okay? We have another graph. And on the horizontal axis, we have year. But in this case, this year is the model year of the car, and that's used as a category. So you can actually have something that looks numerical, but it's really categorical. So there are lots and lots of nuanced differences that you can have. These categories, so to speak, no pun intended, are not hard and fast. So it's really, really important to pay attention to the types of the data. And when you get data from some source to study as part of your investigation, what the author of this data, the person or persons who produced it, what their intent was. Okay. Any questions? Does that make sense? Yeah? All right. Okay, so we talked a little bit about CSV file, and this is the general format of a CSV or comma separated value file. This particular CSV file has all numbers. It's two dimensions. We have a set of rows, row across, going from left to right, and we have a set of columns. Now, the first row has all labels in it, text, and these labels in that first row, that's the so-called header. And these are the variable descriptions of each one of the columns comprising the table. So here we have a variable we're calling X, a variable or measurement we're calling Y1, Y2, and Y3. And as we go row to row, each vector or each row corresponds to a vector or a set of numbers, and they represent an instantiation or a value that each one of these variables can take on. So here we have a numerical variable we're calling X. It takes on a value of 1.96, can take on a value of 6.89, 8.03, etc. And so when we talk about data, we talk about each one of the columns, and in table format, we think of the columns as variables, and we think of the rows as the instantiations of these variables. And so this particular data set listed, this table in our CSV file, it is an instantiation of a 4-vector, and it's all quantitative data. Okay. Any questions? Does that make sense? Yeah. Now, in this next example, we have a table, a CSV file that has mixed data. We have numbers, we have nominal, and we have quantitative data listed. The quantitative data, we have things that are uncountably infinite, and we have things that are discrete. They're countable. And so in this particular case, our first column, date, it's a text-based description of dates and time. We have country, which is a categorical variable. We can't really order countries. We can put it in lexicographic order, but if you're listing out, say, Panama and Canada, there's no natural ordering between the two. We also have units, which is discrete, and revenue, which is continuous. Any questions about this? Does that make sense? And so one of the things to pay attention to when you traffic in data files, certainly it's the file format. And in particular for CSV, when you have mixed data, you have to treat it a little bit differently from if you have pure numerical data or pure nominal data. Okay. Any questions? Excuse me, my voice is going. Any questions? Yes. Mhm. Yes, it wouldn't be mixed. That top line is purely just to label what each column is. And so often, and thank you for asking that, when you think about a CSV file, the header is optional, right? Most of them have headers because they want you to know what the names are for the variables for each of the columns. But you're absolutely right. We talk about what the instantiations can take on. And in this case, the instantiations, let's say this second row, that's the second datum, is mixed between nominal, quantitative. Okay. Any other questions? Does that make sense? Yeah. All right. It's very quiet. Now, many spreadsheets like Microsoft Excel and others will directly convert your spreadsheet data to a CSV file. And moreover, if you were in Windows to double click on a CSV file, it'll ingest it directly into an Excel spreadsheet. And when you deal with Excel, it has not only just the data, but it also has the formatting. So it'll be the font type, if it's italicized, if it's Arial 14 point and all that other good stuff. And when you go to save it as CSV, you'll be doing an export or save as, and Excel is going to flip out. Oh, you're going to lose all your formatting, right? So ignore that because it wants to natively preserve all of that font information and all of that stylistic stuff. And so part of project one, you'll be looking at the spreadsheet files from the organization that contains information monthly about the food prices, and you'll be doing your replacement of missing data inside of the spreadsheet and then saving them for each food item as a CSV file. So don't be alarmed when you get that warning from Microsoft Excel. Any questions? No? No questions. All right. And so this is a design pattern, just a schema. You can think of it as pseudocode that looks eerily familiar or eerily similar to Python. And when you have a CSV file, it's important to be able to read it, bring it into memory off your file system, as well as to write it, the dual operation, to take it from memory and push it into your file system. And so the first thing we have, of course, we're going to import the library, the module CSV, and that pulls in all of the functions or API, application program interface calls that allow you to manipulate CSV files. Now, do you have to use them? No. You could implement all of the parsing, chopping up of the file yourself, the reading and the writing, but it's best just to use the API, right? It's been done. Focus your attention on the important parts of the exercise or task at hand. And so we give it a name, and I'll talk more about file systems, but for now we have a name giving its location, both the directory on disk where it's located, as well as the file name. And of course, the convention is to have this .csv on the end, because that's a hint to you, and also many platforms use that as a hint for an application as to which application is going to be able to read this thing or to write this thing. And so the first thing you do after setting up the location on your file system is you go ahead and you open the file. Now, when you open the file, you're instructing the operating system to go look it up where it's located on the disk and to bring it into a combination of memory and disk. Now, most modern operating systems, your files, when you open them, they straddle two locations. They straddle memory, system memory, random access memory, and your disk. And the reason for that is it's much faster to manipulate, to read or write or insert things that are in memory than it is on disk, because disk often involves mechanical processes. And we'll talk about those more specifically in a few slides. So when you open a file, one of the things you have to specify to your operating system is what your purpose is with this file. Now, when we talk about file systems, we'll learn that the operating system could care less what the name is. That's just for our benefit. The operating system cares about other things that I'll mention in a few slides. But when you use the Open API, you have to tell it whether you want to read or just look at data, or whether you want to write, modify this data. So it's really, really important to get this second part, the spec, right. And notice it's an R in quotes. That means you're opening it for read-only purposes. So if you open the file for read-only purposes, and then you issued a command to write, it's going to say, sorry, permission denied. That's not the permission you have for your interaction with that file, because you told me, the operating system, you want to just examine it, but not change anything in that file. Any questions about this? Does that make sense? You know? All right. So then once you open it, it maintains a data structure, the operating system, in memory, and that's called a file descriptor. And we're capturing that in a variable, in this case, the file. And now with that file, you could absolutely read and write to that, or in this case, read from that file if you choose. Now, what the CSV reader does, you give it a parameter of that file descriptor, and that reader knows how to chop up those columns, and it knows things are separated by a comma, and it knows you could have a header row. So when you use this API, you take the file, the raw file, and then you put a reader around it so that you can interpret it properly. Any questions? That make sense? Yes. Uh, we'll get to that in a moment. Thank you for asking. And so we know that the format of a CSV, the first line has a header, right? And moreover, when you create that CSV reader, it implements something called the iterator interface. And an iterator interface is something for which you can maintain what they used to call in the old days a database cursor. You can maintain a position context, and you can change that position by going through each one of the elements in the underlying list maintained. And so an iterator is a type of design pattern that allows you to move through items that are maintained and backed by a list somewhere in memory. And so here we create a string, an array variable called header, and then we call next. And what next does, it says, I'm going to read that value at whatever the 0th position is in the underlying list, and I'm going to grab it and move the iterator to the next position. And so what I'm doing there is I'm pulling off the header, which is the first row, and I send that to an array called header, because I know that when it takes this first comma separated list, it's going to populate it in an array. And so now that first position, second position, third position that we talked about in the CSV file header, that's going to be in the 0th position, first position, second position of the underlying array called header. Okay. Any questions? No? And so here, rows, this is just my style. I always use the plural, of course, to mean many things. And you'll notice here in this block, I have iteration. I have a loop. I have a for loop in particular. Now with this pattern, you're assuming that the underlying data structure implements the iterator interface. And as an iterator, what this for loop does, you say for, you give it a dummy variable, row in this case, and you say in CSV reader. Now, because CSV reader implements an iterator, it can move through position by position by position, and the for loop will say, aha, there's an iterator there. So for each position I go to in that iterator, the CSV reader, I'm going to set this variable called row to that particular value. So it's going to get the first instantiation or row from the table, the second, the third, the fourth, etc. Each time within the scope of this block, that value row is going to be whatever that particular instantiation was from the table. Now I call it a block because if you take this indented construct, you can kind of draw a rectangle or block around it. So that block has what's called scope. Within that block, anywhere in that block, begun by this for expression, I have this variable called row in existence, and its contents will always be one of the rows from the underlying CSV file. Okay. Any questions about this? So I don't know if they still teach it anymore in intro to programming courses, but one of the things they talk about a program as back in the old days was this idea of basic blocks. And a basic block represents an algorithmic step in your specification of what your program is accomplishing. So here we have a block for opening the file. We have a block for giving us the formatting. We have a block for throwing out the header because we don't need it. We just want the data. We have a block for iteration so we can go through all of the items in that CSV file. And so when you start to think more abstractly of your program as a set of blocks of behavior, when you design your algorithm, you're really just translating each step in your algorithm to a block. Resist the temptation of wanting to go in and write all the details before you understand at a more understood at a higher level what your program is trying to accomplish. Okay? All right, any questions about this? Make sense? And so now here we take our iterator in that for block, and for each round of this iteration, we have our variable row set to each one of the instantiations from our underlying CSV file. And we're going to go ahead and append that to this array. So we have an array called rows, plural, and each position in rows is going to contain an array where that array is an instantiation or a row from that CSV file. All right, any questions about this? Does that make sense? Yeah? All right. And don't be afraid. What the hell was that? All right, I'm gonna close this door. I'm not trying to scare anyone, but I was actually in a real shooter situation once, a previous campus, and it's kind of, SWAT team came through and the whole thing. So sounds like that kind of throw me a little bit. Anyways, all right. Lost my place. Yes. All right. Any questions so far? No questions? All right. So then lastly, after we interact with the CSV reader through our iterator in this for block, we then make sure we close the file. And that's really important to close the file, especially when you're writing. If you were to write to a file and not close it, you'd notice that your changes won't be there on disk. And so when you open a file, your file straddles two locations, memory and disk, because memory is faster. It's trying to optimize on performance. And if you don't close the file, you're not giving your operating system an opportunity to take all the stuff in memory and send it down to disk so that it remains persistent so that you see it again the next time you turn on your machine. All right. Any questions? No? All right. And so this is the dual. This is the write, and it's the same pattern. You give it a path to the file. We have that block. You open the file, but you'll notice here the open spec is a W. That tells the operating system you're going to be making modifications to the file, opening it for write. So when you open it W for write, you can read or you can write it. If you open it just for read, you can only read it. And so you might ask, why do you even have that? Well, if you have multiple processes or programs reading a file, there are optimizations you can make to make it really, really fast if you have a lot of readers, right? So that's why it's there. So then you wrap the writer around the open file. And then here we have a header that we populate as an array. We go ahead, and the first thing we do is we write the header to the file. And then after that, subsequently, we could iterate over writing the data containing instantiations, or there's write rows where you can write the entire table to disk. Any questions about this? Does that make sense? Yeah? All right. So that's a read and a write pattern with CSVs. So let's examine file system. And let's see, we're out at 10:15. We have 20 minutes left, or 20 minutes left. Okay. So in the modern computer system, the so-called von Neumann or Princeton architecture, it's sort of modeled after a vertebrate animal, right? We have what's called a system bus, which is like a spinal cord, and that's a high-speed communication substrate that connects together all of the subsystems that collectively comprise your machine. Now, the von Neumann or Princeton architecture is fairly old. It dates back to the 40s and the 50s. And modern computer hardware is really just a variation of the plain old von Neumann machine. And so here, connecting to our bus, we have the CPU, central processing unit, that does all of your calculations, both logical operations, as well as floating point and Boolean operations. We have our memory, which is our working scratch space, and it's really, really fast. We also have our adapters for something called input-output. And these are associated with devices, things like your keyboard and your mouse, as well as your monitor. So things that allow you to input information and commands into the system, as well as things that allow you to output information. And of course, the whole point of an operating system is to orchestrate and share these finite resources among the many programs running on your system that demand these resources. And so we're going to focus on the disk drive. And the disk drive, how it's presented to you programmatically, is through the so-called file system. Okay. And so it all starts with our ones and zeros, our Boolean representation. And the reason for using binary base 2 representation for information is because underneath the covers in silicon, you represent ones and zeros as the presence of voltage, plus 5 volts, or the absence of voltage, 0 volts. And so when you store information on a disk, you store it magnetically. For a magnetic disk, of course, there's something called solid state. We will just kind of more just mention it, but not talk a lot about it. And so you have a special material called ferromagnetic material. And this material implements a magnet, and you can spread it almost like spray painting onto all sorts of surfaces, things that are more like tape, things that are more like dishes. Now, with this ferromagnetic material, if you pass an electromagnetic magnet over it, you can energize that magnet and change the polarity of the magnet. So you flip where the north side of the magnet is versus the south side of the magnet. And based on that orientation of the north and south pole, you can treat that either as a 0 bit or a 1 bit. Moreover, if you have a conductor that you pass by this magnetic field, you get what's called flux cutting electromotive force, or flux cutting EMF. And what that means is that this moving conductor has electrons inside of it on its valencies, and this magnetic field attracts it and gets those electrons to move. Now, if you have moving electrons, that's what electricity is, right? And so what you can do then is you can pass a conductor over this ferromagnetic material, reading the north poles and the south poles, depending on the orientation, and literally cause voltages or absence of voltage to occur in the conductor and encode that as reading a 0 bit or a 1 bit. And so there's a device called the read-write head that has both a conductor and an electromagnet that allows you to either set the 0 bits or 1 bits, the polarity of these magnetic fields, or to read the magnetic fields, these north poles and these south poles. Any questions about this? Does that make sense? So now we take this ferromagnetic material and we spray paint it, or sputter it, as it's more formally called, onto a type of polymer tape. And now we can move this thing across the whole tape and encode a whole sequence of ones and zeros. And this is our data. And so they did exactly that in the early days. And in the early days of computing, it was before my time, but I still enjoy reading about it. Magnetic tape was the primary storage medium. And it literally looked like a huge spool of tape, and it was coated with ferromagnetic material. And so it had several hundreds of millions of little magnetic fields that you oriented north or south, the polarity that you could read or you could set with this read-write head that I alluded to in the previous slide. But the problem is, this was not random access. You couldn't arbitrarily go to any part of the tape to read certain pieces of data. You had to wind the tape, go all the way to the end to read that part of your file, that data, if it was at the complete end of the tape. So you had a lot of storage capacity, but it was very, very slow. So this is an example of a magnetic tape at the top. And this thing is thousands of yards long on the spool. And you'd put it in a tape machine that you see here on your right. And you put it through a set of pulleys. and you see read-write heads here, and this thing would spin, and it would read the data, or it would write the data. Now, before cloud storage, this was your cloud computing center for your cloud storage. You'd have so-called tape libraries. And I remember when I was like maybe 5 or 6, I saw one. And someone would say, for an organization like Clark, I need the student records from 1945. They would go into the tape library, they'd have them organized, they'd pull the tape for the student records for 1945, they'd load them into this tape reader, and then they'd call up and say, you're ready to go. They would turn it on and they'd read out that data, right? Things are dramatically different now. But these tapes persisted over time, and you can still get tapes now. And in more modern times, they took these tapes, increased the density or the area that these ferromagnetic materials can represent these magnets, north or south pole. And with higher density, you can make it a much smaller form factor. And by putting it inside of a plastic cartridge, you protect it a little better so you can transport it around instead of having to maintain it in a climate-controlled tape storage library. Okay, so you can still get tape drives today for about $200, $250. And the reason why people still use them today, yes, they're slow, but they have a long shelf life and they store a lot of data cheaply relative to more modern mechanisms. So you can get one pretty cheaply, and this is a tape storage cartridge. Here, for about $130, you can get a 5-pack where each one, uncompressed in raw format, is 2.5, 2.5, 2.5 terabytes, and in compressed format, it's where was it? I can't read that. 6.25 terabytes. Terabyte is 2 to the 30 power, right? Megabyte is not a million, it's 2 to the 20, and a gigabyte is 2 to the 30 power, right? So that's a lot of storage very cheaply relative to other drives. And so there are lots of technologies to get that density much, much more fine-grained. And here, this particular tape drive, each tape uncompressed is 12 terabytes, compressed it's 30 terabytes, which is a lot of storage. And in fact, more contemporarily, IBM is always doing research on materials for this and some other concerns. This article is from 2017, it's probably out now. They have tape that can store to 330 terabytes. And that's particularly important when you consider every time things like phones, a new phone comes out, you get a higher density for the pixel representation for the camera. So each picture is taking up more space. And then it's even worse when you have video. So there will always be a need until something else happens, like quantum computing. There will always be a need for high capacity storage. And right now, tape drives are the predominant mechanism that people use. Okay. Any questions? Does that make sense? Yeah? All right. And so hard drives use magnetic platters, and we'll talk about that. And these hard drives increased the speed dramatically at which these things operate. And so a hard drive these days, you can get one cheaply at about 4 terabytes, half a terabyte, 500 gig to about 4 terabytes or so. And they're relatively fast. When you choose a hard drive for your system, what makes them, or what involves additional cost, is all the engineering that goes in for performance type things. And so these platters spin like a record player, they rotate, and the speed of rotation translates directly to the access speed for your data. And so if you were implementing an application that dealt with a lot of data off board, bringing it on board, you'd want something with a very fast hard drive. And don't take my word for it, go on something like Amazon and search for it yourself. If you look at different hard drives, you'll see different drive speeds and other things like that that impact the price. And so one of the important measurements for a disk drive, hard drive, is the so-called seek time and the latency. And I'll talk more directly about what that means. But going back in history, in the mid-50s, this is what a state-of-the-art hard drive looked like. It wasn't something you could carry around on your person or in your backpack. It was something, just to kind of look at the relative size of it, you had to cart it around by airplane, right? And so computing has definitely come a long way just within a generation, which is kind of cool. But this was 5 megabits, which is, you can carry that in your watch now, right? But, we've got a long way. All right. This is a hard drive. This is an 8 terabyte hard drive. A terabyte is to the 30 power. And as you can see, the prices are coming down. Just last year, it was more expensive, about $155 for 8 terabytes. For a regular magnetic drive is pretty darn good relative to just very recently. And so another technology is so-called solid state disks. And a solid state disk uses all chips, all silicon, so there are no mechanical parts. That has benefit for certain applications that need to be ruggedized or that are in difficult environments like satellites, as well as things that go off-road or underwater. But this is much more expensive, and therefore you have less capacity. It is prohibitively expensive to have an 8 terabyte SSD or solid state drive. But the access time is very, very fast, and it's just chips, so there's no rotational latency and no seek time associated with it. And so one of the things when you build a computer, or at least when I build a computer, I don't buy something like a Dell or HP or what have you. I like to choose the parts for my workstations because I have specific needs for the bus speed, for the disk specifications and the processor. And so here, SSDs are really good, especially for the processes that you're going to running for interacting with data frequently, like database types of applications, because there's no seek time and there's no latency. You get a lot of speed. Okay. Any questions? Yes. Ah, because the technology has gotten better. When you look at the fabrication process, they can squeeze many more transistors on the silicon than they used to. And as compute devices proliferate, not just for handhelds and laptops and things like that, but arbitrary devices, you get economies of scale, right? And so in a fab where you might be pushing out, per wafer, you get like, maybe 100 or 200 individual chips off of it. But if you're pressing out, say, 500,000 chips per fab per year, whereas you used to before when there weren't as many computers, 100,000. Just economies of scale makes it cheaper and drives down the cost. Any other questions? No questions? Yeah. All right. And so this is what an SSD. I just talked about. This is an SSD, and again, the prices of these are coming down. You can get a terabyte for less than $100 these days. All right. And so I'm going to motivate, and we only have 5 more minutes roughly. So I'm just going to motivate this next section, and we finish the balance of it on Wednesday. But I don't know, anyone spin vinyl? No? Record players? Yeah. Okay. CDs? You're all streaming, right? Okay. All right. So back in the olden days, when I was a boy, no, we had record players, and a record player was a purely mechanical disc, and it was used to encode the frequencies which comprise sound. And so this is a famous type of record player that goes back to, I think it was the 1800, a Victrola. So if your grandparents have a Victrola, hold on to it. They're worth a lot of money. They're collector's items. And so this particular record, it has grooves in the plastic, and there's a needle that sits in the groove. And as this disc spins, it oscillates that needle, and this needle is connected to a cone, and this cone amplifies the vibrations or the sound for this needle. And so here, hopefully the sound works. The needle is being put down. Where is it? Where's the sound? Oh, come on. There we go. So there's no electronics involved. It's all mechanical. And the reason why I say present this, well, because it's interesting, but also at the time when magnetic discs were being developed, record players were very popular. So when they looked to how they're going to do this, they decided to fashion it after record players. And this is what a magnetic disc looks like. And so you have a bunch of discs here, your platters, and these are just like records, only these things are usually some polymer, and they're coated with this ferromagnetic material. And so you can have little north-south magnets oriented on it, and it's arranged in little grooves around a circle, concentric circles along a platter. And so here you have more than one platter, which is typically the case. And if you look at one of the circles along this platter, you collect them together into what's called a cylinder. And within one circle on the platter, you have a track of ferromagnetic material oriented as these north and south magnets that you can either read the polarity from, or you can use an electromagnet on the read-write head and change the polarity to change it from a 0 bit to a 1 bit or 1 bit to a 0 bit. And so here you have a mechanical arm, and on the end of it is your read-write head, same read-write head we talked about, and it's on a spindle. And so when you want to store your ones and zeros, your binary information, you have to do two things. You have to spin the platter, and it takes time to spin that platter so that you can position the read-write head over the right sector on that particular track for that cylinder. That's called your rotational latency because it takes time to do that. And then you have to take your read-write head and you move it to one of these concentric circles. And so the read-write heads also move, and that's called your seek time. And so the seek time and the rotational latency affect how long it takes you to read data or write data on your disk. That's why you get higher performance when those specifications are smaller. And so a fast seek time might be something like 6 milliseconds, 6/1000th of a second. Any questions about this? That makes sense? Okay. And so I'll end with this. When you store a file, we have a file name, and you saw that file name with the CSV file, and you had a directory name or a folder if you used the Windows, and then you had the file name itself, file name.csv. Now, on your disk, how data is arranged, yes, we have ones and zeros, but those ones and zeros just don't appear arbitrarily. They appear in standard size so-called blocks, like 512 bits consecutively around a track on a platter. And so the so-called sector represents one unit of data because you don't just traffic in individual bits, right? That's inefficient. You want to traffic in a sequence or a so-called block worth of disk. And so when you define a file, all the operating system cares about is what track is the contents of that file on, what sector, and what cylinder, right? That's all it cares about. But it's hard for us to remember track 5, sector 1 through sector 10. It's easier for us to remember file name.csv. And so when you have a file system, how it's organized underneath the covers is you have a name of a file, and that file has allocated to it some number of blocks. Now, those blocks could be sequential around a track, or those blocks could be scattered around the disk. In that case, you have to maintain a list that says, at the end of this block, this is the location of the next block comprising this file. But logically, we have, in this example, file A consists of 4 blocks, file B consists of 3 blocks. And so what the operating system does when you open a file, it looks up in an entry called the file table, that's part of your file system, and it has an entry for the file name, and it has a location of where that file starts, which cylinder, which track, and which sector, and how many blocks on that disk. And so a file is nothing more than a so-called on-disk data structure. It's just an array implementation, but it's not an array implementation like you'd have in Python. It's a special array that's laid out on disk. Okay. Any questions? No questions? All right. So we have 2 minutes left, so we'll stop there, and we'll pick up next time with the balance of this on Wednesday, starting from where we left off. So let's stop the recording.